Okay, ready to dive deep into the world of internet communication. We're tackling the TCP/IP suite today, the engine that makes all those emails, videos, and cat memes possible online.
It's the unsung hero of the internet, that's for sure.
Absolutely. And we're breaking it down into layers, kind of like a cake.
Each layer with its own protocols, like recipes, to get information from one place to another.
So why layers? Why not one giant blob of internet dough?
Well, imagine baking a cake with everything mixed together at once.
Uh-oh, a gooey mess.
Exactly. Layers manage the complexity. Each one in the TCP/IP model has a specific job, working together to deliver data reliably across the internet.
It's all about clean interfaces between the layers, making sure each one does its part without messing with the others.
Exactly. This makes changing or upgrading one layer easier without affecting the others, crucial for the internet's flexibility.
Okay, I'm seeing the brilliance of this layered approach. Now, about the different types of services these layers provide. I read about connection-oriented and connectionless services. Can you give me an example of the difference?
Sure. Think of connection-oriented service, like making a phone call. You dial, connect, talk, then hang up. Data flows in order, just like your words.
Makes sense. So what would be the internet version of sending a postcard?
That's connectionless. You write, address, and send. No need to set up anything beforehand, and the order of arrival isn't guaranteed.
So connection-oriented is like a reliable phone call, ensuring everything arrives in order, while connectionless is like sending a postcard where speed matters, even if it means occasional delays or out-of-order delivery.
Precisely. Each service has its pros and cons, and the choice depends on the application.
Okay, ready to dive into the layers? Let's start at the bottom. The foundation. The physical layer.
This layer is all about the nuts and bolts, the physical media that transmit data. Think copper wires, fiber optic cables, even radio waves.
So all those cables snaking around, those are part of the physical layer.
That's right. It's not just the cables, it's also the signals that travel over them. Electrical pulses, light, or radio waves.
I'm starting to see how this layer literally connects the world, physically transmitting the bits and bytes that make up our online experiences.
And different types of cables have different properties that affect network performance. Remember coaxial cables that weren't originally for the internet?
Really? What were they used for?
Mainly for cable TV. But as demand for faster internet grew, these cables, with their better shielding and bandwidth, could be repurposed for digital transmission.
Wow, that's fascinating. Repurposing existing technologies, so cool.
Absolutely. And another important factor in the physical layer is attenuation.
Attenuation. Even good about signal strength.
Yes. Attenuation is the weakening of a signal as it travels over distance. It's why your Wi-Fi signal gets weaker the farther you are from the router.
That makes sense. So cable type and distance both impact the quality and speed of my internet connection?
Exactly.
Yeah.
Choosing the right physical media is crucial for building robust and efficient networks.
Okay, we have these signals traveling over cables. But what if something goes wrong along the way? How do we make sure our cat memes arrive intact and not a jumbled mess of pixels?
That's where error detection and correction come in, and this is where things get really clever. The physical layer uses special codes to detect and even correct errors during transmission.
It's like a safety net for our data. But how does that actually work?
These codes, like Hamming codes and cyclic redundancy checks, are like mathematical detectives.
Yeah, medical detectives, I love it.
They add redundancy to the information being transmitted. Think of it like sending a message with a checksum at the end. The receiver can use that checksum to verify if the message arrived intact.
So if the checksum doesn't match, the receiver knows there's an error.
Exactly. And depending on the code, it might even be able to correct the error without retransmitting the whole message.
That's impressive. It's amazing how much intricate work goes into making sure our internet experience is seamless. But what happens after the physical layer? Where does our data go next?
Our journey continues to the data link layer, which is like the packaging and delivery service of the internet.
Intriguing. Tell me more about this packaging process.
The data link layer takes the raw bits from the physical layer and packages them into frames, like envelopes for your data. Each frame includes information about where the data came from, where it's going, and how to check for errors, just like a real envelope.
So, adding a shipping label to our data packets.
Precisely. This framing ensures that data is organized and delivered to the correct destination.
Okay, that makes sense. But I'm curious. What happens if two devices try to transmit data simultaneously on the same network? Won't their signals collide, creating a digital traffic jam?
Excellent point. That's a problem, especially in wireless networks, called the hidden terminal problem. It happens when devices can't see each other and end up transmitting simultaneously, causing interference. Think of it like two people trying to talk at the same time on a conference call.
Ah, I've definitely experienced that. So how do we avoid these data collisions in the internet world?
The data link layer uses various techniques. For example, in a wired network like Ethernet, a technique called CSMCD is used.
CSMPD. That sounds complicated.
It stands for carrier sense, multiple access with collision detection, but the concept is simple. Devices listen before transmitting, and if they detect another device transmitting, they wait a random amount of time before trying again. If a collision happens, they both stop transmitting and try again later.
So it's like a polite conversation, waiting for your turn to speak before jumping in.
Exactly. And this politeness ensures smoother data flow on the network.
I'm starting to appreciate the complexity here, how even something as simple as sending data between two devices on the same network involves so much coordination.
And that's just within a single network. Imagine multiple networks connected together, like the vast network of networks that makes up the internet.
Ah, so we're moving beyond individual networks and into the vast expanse of the internet itself. How does data find its way through this complex maze?
That's the job of the network layer. It's all about routing, determining the best path for a data packet to travel from source to destination.
Okay, so the network layer is like the GPS of the internet, guiding our data packets through the digital landscape.
A perfect analogy. And to do this, it relies on IP addresses, unique identifiers for every device on the internet.
So IP addresses are like the street addresses of the internet, telling data packets where to go.
Exactly. And routing algorithms, like Dijkstra's algorithm, figure out the most efficient path through the network, considering things like network congestion and available bandwidth.
It's like finding the most efficient route on a road trip, considering traffic and road closures.
You got it. And just like on a road trip, sometimes there are unexpected delays or detours. That's why the network layer also handles congestion control.
Congestion control. Does that mean preventing those internet traffic jams we sometimes experience?
Precisely. Congestion control mechanisms monitor network traffic and adjust data flow to prevent those digital gridlocks.
So it's like a traffic management system for the internet, making sure everything flows smoothly and preventing major pileups.
Exactly. And these mechanisms are crucial for maintaining the internet's speed and reliability, especially as the number of users and devices keeps growing.
Okay, so we've got our data packaged, addressed, and routed through the internet. What's the next step in this journey?
Now we need to make sure that data gets delivered to the correct applications on the receiving device. That's the responsibility of the transport layer.
The transport layer. It sounds like this layer adds another level of sophistication to the process.
Absolutely. The transport layer is about providing a reliable connection between applications running on different hosts. Think of it like a delivery service that ensures your online orders arrive safely and completely.
I see. So it's not just about getting the data to the right computer, it's about making sure it reaches the right application on that computer.
You're exactly right. And the transport layer is where we encounter two of the most famous protocols in the TCP IP suite, TCP and UDP.
Ah, I've definitely heard of those. But to be honest, I'm a bit fuzzy on the details. Could you give me a refresher on what makes them different?
Of course. TCP, or Transmission Control Protocol, is like a meticulous courier service. It guarantees delivery of data in the correct order and checks for errors along the way. It's like sending a package with tracking and insurance.
That sounds pretty secure. So what about UDP? What kind of delivery service does it offer?
UDP, or User Datagram Protocol, is more like sending a postcard. It's faster and lighter than TCP, but it doesn't guarantee delivery or order. It's like sending a quick message without worrying too much about whether it arrives perfectly intact.
So a trade-off between speed and reliability.
Exactly. TCP is used when reliability is crucial, like for downloading files or browsing websites where you want every bit of data to arrive correctly.
And UDP is better for applications where speed is paramount, even if it means occasional data loss, like streaming video or online gaming.
You got it. A few dropped packets here and there won't ruin your video streaming, but they would be disastrous if you were downloading an important file.
I'm understanding why there are two different protocols at this layer. Different applications have different needs.
Precisely. And both TCP and UDP use fascinating techniques to manage data flow and ensure reliability, even with network hiccups.
Like what? I'm curious to learn more about the inner workings of these protocols.
Well, for example, TCP uses a three-way handshake to establish a connection before data transmission begins.
A three-way handshake. What's that? It sounds very formal.
It is. It's like a formal introduction between the sender and receiver, making sure both are ready to communicate before any data is exchanged.
So it's like making sure both people are on a line before sharing important information during a phone call.
Exactly. And TCP also uses sequence numbers to track the order of data packets, ensuring that everything arrives in the right sequence. It's like numbering the pages of a book.
That's fascinating. These small details contribute so much to the Internet's reliability.
And there's even more. TCP incorporates congestion control mechanisms to manage network traffic and prevent those digital gridlocks we talked about earlier.
This TCP protocol sounds like a real overachiever handling so many tasks.
It is. But that's what makes it so reliable. And UDP, while simpler, also has its mechanisms for ensuring data integrity, just without the guarantees of TCP.
Well, I think we've covered a lot today. We've explored the foundational layers of the TCP/IP suite, from the physical cables transmitting signals to the sophisticated protocols that manage data flow and ensure reliability.
We've laid a strong foundation for understanding how the internet works from the ground up.
Exactly. And I'm already feeling much more knowledgeable about the hidden world that powers my online experiences. But for now, I think we've reached a good stopping point for this part of our deep dive.
Indeed we have. Let's take a break here and pick up our exploration of the TCP/IP suite in the next part of the deep dive.
Stay tuned, folks. We'll be back soon to delve even deeper into this fascinating world of Internet protocols. Welcome back to our deep dive into the TCP/IP suite. Feels like we've already journeyed through the Internet's inner workings, from those physical cables to data packets finding their way across networks.
We have, laying the foundation for understanding how data travels. But now we're ascending to the top floor of our internet cake, the application layer.
The application layer.
Yeah.
That's where it gets interesting for us, right? It's where we actually interact with the Internet, using all the apps and services we love.
Exactly. This is where all the user-facing applications live, the ones we use every day to communicate, browse, share information. Email, web browsers, video streaming, online games, they all live up here.
So it's like the bustling city center of the Internet where all the action happens.
A great analogy. And like a city has different districts, the application layer has a diverse ecosystem of protocols, each designed for a specific task.
Okay, so let's explore some of these Internet districts. I know we talked about SMTP briefly before, the protocol for sending email. Can you remind me how it works?
Think of SMTP, or Simple Mail Transfer Protocol, as the postal service of the Internet. When you hit send, SMTP takes your message from your email client, like Outlook or Gmail, and delivers it to your email server.
So SMTP is like the mail carrier picking up my message and taking it to the local post office, which is my email server.
Exactly. And from there, your email server uses SMTP again to relay the message to the recipient's email server.
So it's like the mail carrier taking my letter to a sorting facility, then another mail carrier taking it to the recipient's local post office.
Precisely. SMTP is used in both legs of the journey, ensuring your email gets from your outbox to their inbox. And once it reaches the recipient's email server, it waits in their inbox until they retrieve it using protocols like POP3 or IMAP.
Oh, so POP3 and IMAP are like going to the post office and picking up your mail.
Exactly. POP3 or Post Office Protocol 3 is like taking all your mail home. It downloads all your emails from the server to your computer.
So with POP3, I have my own pile of mail at home, and it's up to me to organize it.
That's right. But IMAP, or Internet Message Access Protocol, is more like having a P.O. box. Your mail stays at the post office, but you can access it from anywhere.
So with IMAP, my mail is stored securely at the post office, and I can check it from my phone, my laptop, any other device.
Exactly. IMAP also offers more features, like syncing folders and messages across devices, so your inbox always looks the same.
Okay, that's email sorted. Now let's move on to another internet giant, web browsing. How does HTTP, or Hypertext Transfer Protocol, the protocol that powers the web, work?
Imagine you walk into a library and ask the librarian for a specific book. HTTP works similarly. When you type a website address, the browser sends an HTTP request to the web server hosting that website, asking for the page you want.
So the browser is like me, requesting a book, and the web server is like the librarian, fetching it from the shelves.
Precisely. And just like the librarian handing you the book, the server responds with an HTTP response, which includes the page's content.
And that content is written in HTML, the language of web pages, which the browser then displays.
Exactly. It's a request-response cycle, happening every time you visit a website. But what about all those images, videos, and other multimedia elements on web pages?
Right. Web pages are more than just text these days. They're full of multimedia that make them visually appealing and interactive.
And all those multimedia elements are separate files that need to be fetched from the server. Your browser sends additional HTTP requests for each image, video, or audio file, like asking for multiple books.
So my browser's like a busy bee, flitting from request to request, gathering all the files needed to display the page.
That's a great way to visualize it. And this process can slow down the loading, especially for pages with lots of images and videos. It's like waiting for the librarian to gather all the books from different sections.
I've definitely experienced that impatience. Sometimes it feels like forever for a page to load.
Exactly. That's why web developers are constantly trying to make pages load faster, like using smaller image files or compressing data to reduce the amount of information transferred.
So it's a balancing act between making pages visually rich and keeping them lightweight and fast loading.
You got it. It's like a chef trying to create a delicious and visually appealing meal while making sure it's not too heavy or difficult to digest.
Okay, so HTTP is like the librarian, fetching all the information we need to view web pages. But what about cookies? I know websites use them, but I'm not sure what they do.
Imagine you go back to the library and the librarian remembers your name and the books you usually borrow. Cookies work similarly. They're small text files that websites store on your computer to remember things about your visit.
So they're like little memory notes that the librarian keeps to personalize your experience.
Exactly. Cookies help websites remember things like logins, shopping cart contents, or browsing preferences. This makes your online experience more seamless.
That's why websites remember me or keep track of the items in my shopping cart. It's like having a personal shopper.
Exactly. And while cookies can be helpful for personalizing your browsing, it's important to be aware of their privacy implications.
That's a good point. Just like you wouldn't want everyone in the library to know what books you borrow, you should be mindful of the information websites store in cookies.
Absolutely. It's about being informed and understanding how these technologies work.
Okay, so we've explored email with SMTP, web browsing with HTTP, and even touched on the role of cookies. What other essential internet services should we explore in the application layer?
Well, how about file transfer? It's something we all do regularly, whether it's downloading a software update, sharing a large file with a colleague, or backing up photos to the cloud.
File transfer sounds like an essential internet service. What protocol makes that happen?
That would be FTP or File Transfer Protocol. Think of it as a dedicated courier service for moving files between computers.
So when I download a software update, FTP is working behind the scenes, delivering those files to my computer.
Most likely. FTP is specifically designed for transferring files, big or small. And it works similarly to other protocols we've discussed.
So it starts by establishing a connection between my computer and the server where the files are stored.
Exactly. When you start an FTP transfer, your FTP client establishes a connection to an FTP server. It's like calling the courier service and saying, hey, I need to send a package.
And once connected, I can browse the server's directory, choose the files, and initiate the transfer, right?
That's right. And like with a courier service, you specify the delivery address, which is your computer.
So it's like filling out the shipping label and sending the package on its way.
A perfect analogy. And FTP is versatile. It handles both uploading and downloading, just like courier service can handle pickups and deliveries.
And like physical packages, there are different ways to handle different types of content, right? I wouldn't want delicate china shipped the same way as a box of books.
That's a great point. FTP has different modes of transfer, like binary mode for files like executables or images, and ASCII mode for text files.
It's like choosing the right packaging and shipping container to ensure the contents arrive safely.
Exactly. And like with physical shipping, file size, transfer speed, and security are important when using FTP.
Okay, so we've covered email, web browsing, and file transfer. That's a lot covered in the application layer. What are some other key players in this internet city?
There are many other protocols up here, each with its own function. There's Telnet for remote access to computers, SSH for secure shell connections, and even protocols for streaming audio and video.
It's amazing to think about all these protocols working together seamlessly to power our internet experience.
It truly is a testament to the TCP/IP suite's design. The application layer wouldn't be possible without the foundation laid by the layers below.
So it's like a well-designed city with a robust infrastructure that supports a thriving community.
A perfect analogy. And like a city is always evolving, the application layer is constantly changing as new applications and services emerge.
You mentioned that the application layer is constantly evolving. What are some of the challenges in designing these protocols that need to keep up with the internet's changing demands?
That's a great question. One of the biggest challenges is security. The application layer is the most vulnerable to attacks, as it's where data is exchanged and processed.
I can see why that would be a concern. With all this sensitive information flowing through the application layer, like emails, passwords, financial transactions,
Yeah.
security is paramount.
Absolutely. That's why many application layer protocols use encryption and authentication to protect data confidentiality and integrity.
So it's like adding locks and security systems to those internet districts, keeping our valuable data safe.
Exactly. And like in the physical world, security is an ongoing battle. As new threats emerge, security protocols must constantly evolve.
It's a constant arms race between the good guys and the bad guys in the digital world.
You could say that. Another key challenge in application layer design is performance optimization. With the increasing demand for faster and more responsive applications, developers are constantly seeking ways to streamline data transfer and minimize latency.
Latency, that's the delay between sending a request and receiving a response, right?
Right. Exactly. Reducing latency is especially important for things like video streaming and gaming, where even a slight delay can ruin the experience. Imagine a live stream that keeps buffering, or a game where your actions lag.
That would be incredibly frustrating. So it's a balancing act between security, performance, and keeping up with evolving demands.
Precisely. And that's what makes the application layer so dynamic and fascinating.
Well, I'm seeing the application layer in a whole new light. It's not just a collection of apps. It's a vibrant ecosystem of protocols, each shaping our online experiences.
And like any ecosystem, it's constantly evolving and adapting to new challenges and opportunities.
Well, I'm eager to delve deeper into this world and learn more about the protocols that power our favorite internet services. But for now, I think we've reached a good stopping point for this part of our deep dive.
Indeed, we've laid the groundwork for understanding the application layer and its vital role. Let's take a break and continue our exploration in the final part of the deep dive.
Join us next time as we venture further into the application layer, uncovering the inner workings of some popular internet protocols, from email to web browsing to file transfer. It's going to be a fascinating journey. Welcome back to the final part of our deep dive into the TCP/IP suite. We've journeyed through the physical and data link layers, explored the network and transport layers, and now we're back in the bustling city center of the internet, the application layer.
Where we interact with all those applications and services that make the internet so indispensable.
Exactly. I'm excited to take a closer look at some of those applications, starting with email. We've touched on SMTP, but can you walk me through the whole email journey? How does my message go from my outbox to the recipient's inbox?
Absolutely. Imagine you're writing a letter and want to send it across the country.
Okay, got my pen and paper.
First you write, address the envelope, and add a stamp.
That's SMTP in action, right? Simple mail transfer protocol.
Precisely. SMTP is like your mail carrier, taking your message from your email client, like Outlook or Gmail, and delivering it to your email server.
So SMTP is like taking my letter to the local post office, my email server.
Exactly. And just like a post office sorts mail, your email server uses SMTP, again, to relay the message to the recipient's email server.
It's like my letter going from the local post office to a sorting facility, then another mail carrier taking it to my friend's local post office.
Perfect analogy. SMTP ensures your email travels through the internet, from your computer to their inbox.
Okay, so SMTP is the delivery truck. But what happens when the email reaches my friend's email server? How do they retrieve and read it?
That's where POP3 and IMIC come in. Think of them as different ways to pick up mail.
Okay, I'm intrigued. Tell me more about these mail retrieval options.
POP3, or Post Office Protocol 3, is like going to the post office and taking all your mail home.
So all emails are downloaded from the server to my friend's computer.
That's right. It's simple, but it has limitations. What if your friend wants to check email from their phone or a different computer?
Ah, I see the problem. Their emails are tied to that one computer.
Exactly. That's where IMAP comes in. IMAP, or Internet Message Access Protocol, is like having a P.O. box.
So their mail stays securely at the post office, but they can access it from anywhere.
Precisely. With IMAP, they can check email from their phone, laptop, any device with internet.
That sounds much more convenient. Is there anything else IMAC can do?
Yes. IMAP also syncs folders and messages across devices. So if they create a new folder on their phone, it'll also appear on their laptop.
So it's like a single unified inbox, always up to date.
Exactly. That's why IMAP has become the preferred protocol for many, offering convenience and flexibility.
Okay, that's email. Now let's talk about web browsing. I know HTTP, or Hypertext Transfer Protocol, makes the web work, but I'd love to understand the step-by-step process.
Imagine walking into a restaurant and looking at the menu.
Okay, I'm picturing a delicious menu.
You choose a dish and place your order with the waiter.
That's me sending an HTTP request to the web server, right? Telling you which page I want.
Precisely. Your browser is like the waiter taking your request to the kitchen, the web server.
And just like a chef prepares the dish, the web server gathers the information to create the web page.
Exactly. The web server assembles the text, images, videos, and other elements, all formatted in HTML, the language of web pages.
So HTML is like the recipe, telling the browser how to display the page.
Great analogy. Once the page is ready, the server sends it back to your browser, like the waiter bringing your meal.
And my browser displays the web page on my screen.
It's a request-response cycle happening every time you click a link or type an address.
Okay, that makes sense. But what about images, videos, and multimedia? Are they all included in that single response?
That's a great question. While some basic elements might be included, larger files like images and videos are often fetched separately.
So it's like the waiter bringing your main course first, then side dishes and drinks.
Exactly. Your browser sends additional HTTP requests for each image, video, or audio file, and the server responds with those individually.
So it's like a multi-course meal.
Yes, that's a great way to see it. This ensures the most important content, the text and layout, arrives first, while larger files load in the background.
Okay, so HTTP is like the waiter. But what about cookies? I'm still a bit fuzzy on their purpose.
Imagine going back to that restaurant and the waiter remembers your usual order and table.
That would be great.
Exactly. Cookies work similarly. They're small text files that websites store on your computer to remember things about your visit.
So they're like personalized notes for a more tailored experience.
Precisely. Cookies store information like logins, shopping cart contents, browsing preferences, or recently viewed items.
That's why websites remember me or my shopping cart. It's like having a personal shopper.
Exactly. And while cookies enhance your browsing experience, it's important to be aware of privacy implications.
Right. It's like that friendly waiter knowing a bit too much.
Exactly. It's important to be mindful of the information websites store in cookies and adjust your browser settings if you want to limit tracking or clear them.
Okay, we've covered email, web browsing, and cookies. Now let's talk about file transfer.
Think of file transfer as the postal service for digital packages. Whether you're downloading a software update, sharing a large file, or backing up your photos, you're relying on FTP or file transfer protocol.
So FTP is like the cargo ship of the internet, transporting digital containers.
Great analogy. Just like a cargo ship needs a destination, you need the address of the FTP server where the files are.
So I need the server's IP address or domain name to start an FTP transfer.
Exactly. You'll also need the login credentials, unless it's a public server.
It's like having the right shipping address and keys to the warehouse.
Precisely. Once connected to the FTP server, you can browse its directory structure, like exploring a warehouse.
So I can see all the files and folders and choose what to download or upload.
Exactly. FTP allows transfer in both directions.
Like a two-way shipping lane.
A perfect analogy.
Yeah.
And like physical cargo, there are different ways to handle different types of digital content.
Right. Different packaging for different items.
Exactly. FTP offers different transfer modes, like binary mode for executables or images, and ASCII mode for text files.
Choosing the right packaging for safe arrival.
Precisely. And like physical shipping, file size, transfer speed, and security are important when using FTP.
Okay, we've explored SMTP for email, HTTP for web browsing, and FTP for file transfer.
And we've only scratched the surface. The application layer is vast and diverse, always evolving.
It's amazing to think about all those protocols working behind the scenes, enabling us to communicate and explore the digital world.
It's a testament to human ingenuity. The TCP/IP suite, with its layered architecture and protocols, has revolutionized how we connect.
And it all started with a simple idea, transmitting data between computers reliably and efficiently.
And from that, a global network was born, connecting billions of people and devices.
It's amazing to think about the impact of the TCP/IP suite on our lives. It's the invisible force behind our online experiences.
And as we innovate, the TCP/IP suite will continue to evolve, ensuring we stay connected in a changing digital world.
I'm so grateful for this deep dive. It's given me a new appreciation for the internet.
And remember, this is just the beginning. There's a whole universe of protocols and technologies out there.
To our listeners, thank you for joining us on this journey through the TCP/IP suite. We hope you've gained a deeper understanding of the system that connects us all.
Keep exploring and keep shaping the digital world we share.